First talk today is from Ben Farr from the University of Colorado, representing a group from a number of different places, including John Gorey from University of Iowa and Shobhan and Ulf Israelson from JPL. But Ben Farr, it's your floor.
Awesome, thank you. Yes, so thanks everyone for coming to listen to my talk. We have been doing some experiments for dust mitigation for lunar surface exploration. So we can go ahead and go to the next slide and actually get started. So first off, the motivation for the experiment is, of course, that lunar regolith and dust has been a big issue ever since we've been trying to go to the moon. So it causes issues for spacesuits, it causes damages to solar arrays, it reduces the efficiency of thermal radiators, and it also is really, really bad for us to breathe in. So it's something that we certainly need to be getting rid of, and that's what we've been working on it for a while. And hopefully we are finding a solution. So if we go to the next slide, I can start talking about the solution. So our experiments are based on something that was developed by Dr. Wang several years ago and is called the patch charge model. So the patch charge model is based on the idea that there are small microcavities between dust particles, individual dust particles, and those microcavities actually absorb what's called secondary electrons or photoelectrons that are emitted from the neighboring particles. And then once they absorb enough electrons, then that builds up a really, it gives us a large buildup of negative charge, which eventually causes the dust particles to jump away from each other. And it's that we're using, it's that theory that our experiments are based on to try and remove dust from surfaces. So could we go to the next slide, please? So our experiment specifically, we are using an electron beam to try and remove dust. The electron beam is just our agent to cause that charging of the particles. So our experiments are done inside of a cylindrical vacuum chamber, pretty small, about 50 centimeters in diameter and about 28 centimeters high. We've been using JSC1 lunar simulant as our dust that we test. And to test it, we sift the dust onto a substrate. So we've tested a whole bunch of different materials. We tested glass, spacesuit, solar panels. That's all we're talking about today. So we've tested several materials. And inside the chamber, the material is tilted 45 degrees relative to the filament. And the filament puts out a 80 to about 230 electron volt beam that's emitted from a hot filament with a negative bias. And all the tests are performed in vacuum. And then to record the data, we just use a video camera. So we start off by taking a picture of the sample 100% covered in dust. Then we take a picture of the sample completely clean. And then we record the dust as it sheds off of the material. And then to actually come up with a number for our results, we just we subtract the images basically, and that gives us the coverage throughout the test. And can we go to the next slide, please? All right, so this is just a quick little video that I'd like to show you guys actually. So if you could play the video real quick, that'd be awesome. So this is just dust on a substrate while exposed to an electron beam, and you can see that it's going absolutely crazy. This sample in particular is just completely flat so that we can get a better video, but it kind of shows how much the dust is actually reacting to the electron beam. And then there's a few more images on this slide as well, if you could show those. And these show just the before and after pictures of a glass sample covered in dust. So you have the before image on top and then the after image on the bottom. So it's actually really, really good contrast, and shows that we get about 75% cleanliness after this process. So we're very happy with it so far. Can we go to the next slide and we'll start talking about the results. So for our first experiment, we wanted just to test, first off, if the theory actually worked at all for dust mitigation. We wanted to test what the optimum beam parameters would be, and we wanted to test several different materials and see how they all reacted to the cleaning process. So this first slide shows our electron beam current density. So we ran a whole bunch of tests, all with 230 electron volts, and we tested a bunch of different current densities. So from 0.3 microamps per centimeter squared up to 6.1. And what we found is that for 0.3, we get a little bit less cleaning than some of the others, but everything above that, we get about the same amount of cleanliness for the final result. The only difference is that it takes a little bit longer to get there. So the higher the electron current density, then the quicker it cleans off. But we also found that for about 3 microamps per centimeter squared, it's all about the same. So that's what we stick with for most of our testing nowadays, just because it saves a little bit of power. Yeah, can we go to the next slide, please? Thank you. And this slide is testing the electron beam energy, where we tested 80 electron volts, 150 electron volts, and 230 electron volts. And we were expecting that we would get a little bit better result with more and more energy, and that's exactly what we found. So we found that it's a little bit better the higher the energy goes. Up to a certain point, we did run some extreme cases with like 400 electron volts, and we didn't find those to be any better than 230, so that's where we stick for the rest of our testing. Next slide, please. We also tested several different surfaces in our first experiment. So we tested glass and spacesuit and found that the glass is a little bit easier to clean than the spacesuit. And that we believe is just because the spacesuit is full of little cavities and deformities and irregularities in the actual surface the dust can get stuck in. And that's why we think it's a little bit harder to clean. But overall, with the glass and the spacesuit, we're very happy. Can we go to the next slide? And we also tested the dust layer thickness and how that influenced the final cleanliness. So we ran one test where it starts off 100% covered, one where it starts off 60% covered, and then one where it starts off 40% covered. And we found that the thinner and thinner the layer was, the initial dust layer, the easier it was to clean off. So for a very thick dust layer, the max cleanliness we got was about 55. Kind of in the middle, we got about 70%. And then for the thinnest layer that we tested, we got about 85% cleanliness, which checks out. We were assuming that it would be a little bit harder to clean thicker dust layers just because it gets a little bit more compacted on the surface and driven in there. Next slide, please. So from that first experiment, the results that we came away with is that the optimum electron beam parameters are about 230 electron volts with an emission current of 1.5 microamps per centimeter squared. And then with those parameters, we were able to clean a glass sample up to about 80%, and then a spacesuit sample up to about 75%. And that's for a thin initial dust layer, so 60% covered to start. Next slide, please. So what we're working on now is getting rid of that last 20 to 25% of dust that remains on the sample after we perform the cleaning process. So the method we're investigating right now is actually changing the angle between the dust and the electron beam, and that's to try and expose different microcavities basically to the electron beam. And you can see that in the image on this slide as well. So we've been running tests with glass, spacesuit, and a photovoltaic solar panel, and we ran tests starting at 0% cleanliness and 40% cleanliness. So I can talk about those results real quick after I talk about the setup on the next slide. So the setup for the second experiment was basically the same as the first one, except that we put our sample, we connected it to a DC motor that rotates it at about 6 RPM. So the process of the test is we would run the experiment just like the first one. So we would leave it completely stationary, 45 degrees to the filament, and we would let it go up until the activity stopped. And then once it stopped, then we would rotate the sample for 2.5 minutes, and then we would hold it still for 2.5 minutes. And in that stationary 2.5 minutes is where we would take our data. And the reason we split it up into the stationary segment at the beginning and the rotating segment at the end is just so we could try and actually see a jump from where the rotating actually helps. And we also, before we started taking data and everything, we did run a few tests where we had no electron beam and we just rotated the sample to see if any dust falls off just because of gravity or vibration or something like that. And we did not find that anything fell off. So we were confident that any increase in cleanliness was because of the changing angle. So the next slide would be awesome. Okay, so here are the results for the glass sample. So the blue curve, that is for a thin dust layer, and there's a little black mark on the plot that shows where the rotation starts. So for the blue curve, you don't see too much of an increase with the rotation. And we think that's just because it was already pretty clean to start. There wasn't that much more dust to come off, and then what was left is very hard to remove. So we got about 88% before rotation and maybe 92% after the rotation. So it's a little bit of an increase, but not too much. The red curve is for a thicker dust layer, and that shows a much better increase with rotation. So we got to about 65, 70% before the rotation, and then after the rotation, we bumped up to about 80, 85%. So that was actually really, really good for us. Next slide, please. Oh, just to clarify, the electron beam is turned on during the rotation. So on all these slides, the electron beam is turned on throughout the duration of the test. So this is for the spacesuit. And for the spacesuit sample, we actually found that we got a pretty good increase in cleanliness for both the thin layer and the thick dust layer. So both of those tests came out to a final cleanliness of about 85% after the rotation. So we're really pretty happy with that. The rotation showed a big increase in the cleanliness. Next slide, please. And then the solar panel was a little bit more troublesome. We found it to be very, very sticky. So for the thick dust layer, we saw that before the rotation, we got to about 42%, and then the rotation bumped us up to about 50% cleanliness. So really not that great. We're still working on that. And then for the thin dust layer, we saw almost no increase in cleanliness with the rotation. So basically, we just found out that the solar panel was very, very sticky for the dust, and we are still working on why that is necessarily. But that's the results from the first test. Not too much increase with rotation for the solar panel. Next slide, please. So the summary for our results is that we're confident that we can use the electron beam to clean dust off of the surface. We found that 230 electron volts is a good energy, and 1.5 microns per centimeter squared is a good current density for the beam parameters. And with those, for a stationary sample, we can reach about 75 to 85% cleanliness for spacesuit and glass with less than 25 micron dust. And then we found later on that we can remove an additional 10 to 20% if we rotate the sample. And then we found that the solar panel, the maximum cleanliness we can get is about 50 to 60% cleanliness, even with the rotation. So, and then in future experiments, we're going to test just using multiple electron beams rather than rotating the sample. This is just to make the process a little bit simpler. So we have 3 electron beams, each oriented differently, so to try and imitate the rotating without actually rotating. And then we're also in the future going to test a bunch of different materials. We're going to test ITO-coated glass, thermal blanket, Kapton tape, aluminum, stainless steel, and whatever else we can think of. And then way in the future, we're also going to test and see if this might work in a Martian environment, or figure out how we can adapt it to work in a Martian environment. And that's all I've got. Thank you, everyone, for listening.
Okay, we do have some questions in the chat that we'll try to get to some of them here. The first question is from Christine Hartzell on the effect of the angle of the plate. I think that's sort of been dealt with in your presentation, but if she wants to come back, maybe I've misread that.
So for the stationary sample, it's at 45 degrees relative to the filament. And then when we rotate it, and then every time we stop to take data, we stop at 45 degrees as well. So that every time we're actually taking data that we analyze, that's all taken at the same angle, so 45.
All right. Dennis Gallagher asks, how would removal be influenced by the mechanical stricture of lunar dust on the astronaut suit fabric? So I guess you've talked about stricture in a couple of places. But.
So that, I think I understand the question. So the dust really does get kind of tangled up in the actual threads of the fabric, and that's why we're trying to do the rotating method and see if we can get different angles and get the dust to come out of those pockets that it gets tangled up in. But we haven't done any specific research to see like how exactly the dust is getting tangled up. I'm not sure if that answers the question exactly, but.
Okay, and then the last one we'll try to cover here before we have to go is how exactly are you defining cleanliness?
So the cleanliness, we are defining it just by percentage of coverage of dust. So like I said at the beginning, we take a picture of the sample completely clean and a picture of it completely covered in dust. And then we use those to contrast against the images we take throughout the test. So cleanliness is effectively coverage at best.
Okay, well, that's great.